Arrhenious equation. Arrhenious equation is a formula for the temperature dependence of the reaction rate. So, Arrhenious equation will actually give us the dependence of the rate constant of a chemical reaction on the temperature, pre-exponential factor, and other constants of the reaction. So the basic use of this formula is to calculate the energy of activation, and it will justify the effect of temperature on rate of the reaction. That is what we call it as the Arrhenious equation. And this equation is a very important concept of chemical kinetics. Hence, Arrhenious equation is K is equal to A e to the power of minus EA by RT, where K is the rate constant, T is the absolute temperature, A is the pre-exponential factor, EA is the activation energy for the reaction, and R is the universal gas constant. So, the point to make a note is T is the absolute temperature, which will always be in Kelvin. And hence, we plot a graph, or we say it as a Arrhenius plot. It is a graph or it is a plot which is obtained by plotting the logarithm of rate constant K with respect to the inverse of the temperature, that is 1 by T. And the result is the negatively sloped line, and that is useful in finding the missing components of the Arrhenious equation. Hence, Arrhenius plot is also a very important part of Arrhenious equation. And next, based on the Arrhenious equation, we have another formula, that is 2-point form of the Arrhenious equation. That is, the activation energy can also be found algebraically by substituting two rate constant K1 and K2 and the two corresponding reaction temperatures T1 and T2 into the Arrhenious equation. So when we take the basic, that is ln K is equal to minus EA by RT plus ln A. Here, with respect to rate constant, that is 2 rate constant, if I take, K1 becomes is equal to minus EA by RT1 plus ln A, and ln K2 will become is equal to minus EA by RT2 plus ln A. Hence, now if I subtract the equation 4 from equation 3, we get as ln K1 by K2 is equal to EA by R into 1 by T2 minus 1 by T1. We can rearrange this equation in order to calculate the activation energy. So, we get as EA is equal to R T1 T2 by T1 minus T2 ln of K1 by K2. And this formula is also being used in order to solve n number of numericals. So now let us take for example and the question is the rate constant for the reaction H2 plus I2, which is giving 2HI, is 5.4 into 10 to the power of minus 4 at 326 degrees Celsius, and at 410 degrees Celsius the rate constant was found to be 2.8 into 10 to the power of minus 2. So here we have to calculate the activation energy. So rate constant is exponentially dependent on the temperature, and we know the rate constant for the reaction at two different temperatures can be calculated using this formula, that is ln K1 by K2 will become is equal to EA by R into 1 by T2 minus 1 by T1, and hence we can calculate the activation energy with the help of this formula. But the point we have to make a notice, the temperature which they have given is in degrees Celsius. Hence our first task should be to convert the temperature into Kelvin, and then only we are supposed to use it in our equation. Then only we should be substituting the value in this equation and we could arrive at the answer. So we can substitute the value of K1, K2, which is given as 5.4 and 2.8. So we could substitute that. That will be equal to minus EA by R, and 326 and 683 is the two different temperature which we have converted into Kelvin, and then from that we could calculate the value of EA, and we get the answer as EA is equal to 1.60 into 10 to the power of 5 joules per mole.